Welcome to the lecture on job sequencing and replacement theory. This lecture is for chapter 4 of our course Operations Research. In this chapter, we will discuss the problem of sequencing of job in which a number of jobs are to be performed on different machines, so that the total time elapsed time is minimized or total cost is minimized. There are several sequencing problems in the world. All sequencing problems cannot be solved. In this chapter, we will discuss only a few types of sequencing problem which will be solved by developing some algorithm. And naturally, the solution will not be always the optimal, but anyway we will get near optimal or very good solutions by applying all these algorithms. In this chapter, we will also discuss the problem of replacement, and which is concerned with the situation when a machine or equipment needs to be replaced due to decreased efficiency or failure. The whole content of this chapter will be covered in 4 modules. The first 2 modules will be devoted to job sequencing, and the next 2 modules will be devoted to replacement problem. So, let us now start our discussion on module 1 of this chapter. Let me first explain where is the problem in job sequencing. Suppose that we have 2 or 3 jobs which are to be processed on 2 machines. It may be done by the method of enumeration, in which we can calculate the total time or cost and search for that sequence which consumes the minimum time or cost. If the number of jobs or machines increases, then the problem becomes complicated. It cannot be done by the method of enumeration. As you know, if we have n machines and m jobs, then we have factorial n whole to the power m possible sequences. For n equal to 5 and m equal to 5, we have clearly factorial m whole to the power 5, that is 25 into 10 to the power 9 possible sequences. The number of sequences here is very large. Therefore, it is time consuming to find all the sequences and select the optimal one among all these sequences. Hence, we have to go for an easier method for finding the optimal sequence. Before we proceed for a method for finding the optimal sequence, let me explain some terminologies which are usually used in job sequencing. Processing time. This is the time required by each job on each machine. Processing order. This refers to the order or sequence in which machines are required for completing the job. Idle time. This is the time during which a machine does not have a job to process. Total elapsed time. This is the time interval between starting of the first job and completion of the last job, including the idle time if any, in a particular order by the given set of machines. No passing rule. This means that the passing is not allowed, that is, the same order of jobs is maintained over each machine. If n jobs are to be processed, through two machines A and B in the order A B, then this means that each job will go to machine A first and then to machine B. Now, let me define some assumptions which are called principal assumptions for job sequencing problems. We assume that the processing time on each machine is known. The time required to complete a job is independent of the order of jobs in which they are to be processed. No machine can process more than one job simultaneously. We also assume that the time taken by each job in changing over from one machine to another is negligible, and each job once started on a machine is to be performed up to completion on that machine. The order of completion of job has no significance at all, that is, no job is to be given priority. A job starts on the machine as soon as the job and the machine both are idle. So, these are the principal assumptions which we usually made in job sequencing problem. Types of sequencing problems. There are various types of job sequencing problems arise in the world. All sequencing problems cannot be solved. Here we considered the following 4 types of job sequencing problems. In type 1, n jobs are to be processed on 2 machines, say machine A and machine B in the order A B. This means that the job is to be processed first on machine A and then on machine B. In type 2, n jobs are to be processed on 3 machines A, B and C in the order A B C, that is, first on machine A, second on machine B and third on machine C. In type 3, n jobs are to be processed on m machines in the given order, and in type 4, 2 jobs are to be processed on m machines in the given order. Now, we proceed to discuss on type 1 job sequencing problem, that is processing of n jobs through 2 machines. Suppose that n jobs are to be processed on 2 machines, say A and B. Each job has to pass through the same sequence of operations in the same order, that is, passing is not allowed here. Let AI be the processing time for ith job on machine A and Bi be the processing time for ith job on machine B, where capital T is the total elapsed time. Then our problem is to determine the sequence in which n jobs should be processed through machines A and B, so that the total elapsed time capital T is minimum. To solve this problem, we would like to take help of Johnson's algorithm. Johnson's algorithm has some steps. In the first step, we have to select the minimum processing time out of all AIs and BIs. If it is AR, then do the Rth job first, and if it is BS, then do the Sth job at last. Step 2. In case of a tie, we have three options. If the minimum of all the processing times is AR, which is also equal to BS, that is minimum of AIBI equal to AR equal to BS, then do the Rth job first and Sth job at last. Now, if minimum of AIBI equal to AR, but AR is equal to AK, that is there is a tie for minimum among AIs, then select any one. And if minimum of AIBI equal to BS, but BS equal to BT, that is there is a tie for minimum among BIs, then also select any one. Step 3. Now, eliminate the job which has already been assigned from further consideration and repeat steps 1 and 2 until an optimal sequence is found. Johnson's algorithm concentrates on minimizing the idle time of machine. It is proved that optimal sequence of n jobs which are to be processed on two machines A and B in the order AB necessarily involves the same ordering of job on each machine. The total elapsed time is minimum when the sequence of jobs is same for both the machines. Now, we will take an example to show how Johnson's algorithm can be applied to solve a type 1 job sequencing problem, that is processing of n jobs through two machines. Suppose that there are 5 jobs, job 1, 2, 3, 4 and 5, each of which has to be processed on two machines A and B in the order AB. Processing times in hours are given in the following table. For job 1, 2, 3, 4 and 5, processing times on machine A are 6 to 10, 4 and 11 respectively, and processing times on machine B are 3, 7, 8, 9 and 5 respectively. We have to determine a sequence in which these jobs should be processed so as to minimize the total processing time. If we apply Johnson's algorithm, then we have to first look for the minimum processing time. So, this table shows that the minimum processing time is 2, which corresponds to job 2 on machine A. So, the allocation of jobs will start by placing job 2 at the first place of the sequence. Now, we eliminate job 2 from the table, and then the reduced set of processing times is as shown below. Now, we have 4 jobs 1, 3, 4, 5 and their processing times on machine A and B are shown in this slide. Now, following Johnson's algorithm, we have to again look for the minimum processing time, this table shows that the minimum processing time is 3 hours, which corresponds to job 1 on machine B. Therefore, job 1 should be placed at the end of the sequence. Now, again we will find the reduced set of processing time by eliminating job 1, and now we have only 3 jobs, job 3, 4 and 5, and if we follow the same technique, finding the minimum processing time, then ultimately we will get the optimal sequence as 2, 4, 3, 5, 1. From this optimal sequence, we can find the minimum elapsed time, and for this we compute the results as shown in the table. We have the job sequence 2, 4, 3, 5 and 1, and then for machine A we have time in and time out. Time in 0 indicates that the job 2 starts at 0 time and job 2 is completed on machine A after 2 hours, and until the job 2 is finished on machine A, machine B remains idle. As soon as job 2 is completed on machine A, machine B starts working, and in this way, when the sequence of jobs 2, 4, 3, 5 and 1 is completed on machine A, we need 33 hours, and these jobs will be completed on machine B after 36 hours. Therefore, we need the minimum elapsed time is 36 hours. Now, we can also calculate the idle time for machine A and machine B. As we can see that all the jobs are completed on machine A in 33 hours, but the machine A has to wait until the jobs on machine B are completed, that is until 36 hours. Hence, the idle time for machine A is 3 hours. And to compute the idle time on machine B, we see that when the job 3 on machine B is completed, it is 26 hours, and then the machine B has to wait for 1 hour to start processing job 5, because job 5 was not completed on machine A then. Similarly, machine B has to wait 1 hour at the end of processing job 5 when it completes at 32 hours. So, machine B has to wait 1 hour to start processing job 1 as soon as the job on machine A is finished. So, total idle time for machine B will be then initially 2 hours, and then in the subsequently 1 hour and 1 hour. So, the total idle time for machine B is 4 hours. Let us take another example. A bookbinder company has one printing machine and one binding machine. There are manuscripts of a number of different books. Processing times for printing and binding are given in the following table. We have to determine the sequence in which books should be processed on the machines so that the total time required is minimum. Following Johnson's algorithm, we look for the minimum processing time, which is 1 hour, and it corresponds to book B on printing machine. Therefore, the B will take the first place in the sequence, and then proceeding similarly as we have explained already in the previous example, we can find the optimal sequence as B, D, C, E, A, and the minimum elapsed time can be obtained by finding out the time in and time out for each machines, printing machines and binding machines. And from the table we see that the minimum elapsed time is obtained as 30 hours. Idle time for printing machine is 30 hours minus 20 hours, 2 hours, and idle time for binding machine is equal to 3 hours. Let us consider another example. There are 7 jobs, each of which has to processed on 2 machines A and B in the order AB, and processing times are given in the following table. We have to determine a sequence of these jobs that will minimize the total elapsed time. Also, we have to find the total elapsed time and idle times for machines A and B. The smallest processing time, as can be seen from this table, that the minimum processing time is 1, which corresponds to job 6 on machine B. Therefore, job 6 should be placed at the end of the sequence. Then the reduced set of processing times is shown in this table. Now we have only 6 jobs. We have already eliminated job 6 from this table, and then we look for the minimum processing time, which is 3, and the minimum processing time 3 corresponds to job 1 on machine A as well as job 7 on machine B. So, according to Johnson's rule, then job 1 is to be scheduled first and job 7 should be scheduled next to 6. Now, we consider the next reduced set of processing times, which are shown in the following table, and again we look for the minimum processing time, which is 6, and the minimum processing time corresponds to job 4 on machine A as well as job 4 on machine B. Therefore, we may choose arbitrarily to process job 4 next to 1 or next to job 7. Therefore, we have 2 sequences as shown in the slide, and the remaining jobs are to be selected from the reduced set of processing times as shown in the slide. We have now 3 jobs, 2, 3 and 5, and the minimum time processing time is 10, which corresponds to job 2 on machine B, job 3 on machine B, and job 5 on machine A. According to rules, job 5 is scheduled next to job 4 in the first sequence or next to job 1 in the second sequence. Job 2 is then scheduled next to job 7 in the first sequence or next to job 4 in the second sequence. Thus, we obtain the optimal sequences as 1, 4, 5, 3, 2, 7, 6 and 1, 5, 3, 2, 4, 7, 6. On the basis of these optimal sequences, we can find the total elapsed time. For the first sequence, this slide shows the total elapsed time is 67 hours, and for the second sequence, the total elapsed time is also 67 hours, and the idle time for machine A is here 1 hour and the idle time for machine B is 17 hours. Until now, we have discussed some basic terminologies and principal assumptions of job sequencing problems. We have explained that though there are many sequencing problems exist in the world, we will concentrate only on a few types of job sequencing problems. Here we will concentrate on 4 types of job sequencing problem. We have already discussed type 1 job sequencing problem, that is processing of n jobs on 2 machines, and we have also taken some example to show how Johnson's algorithm can be applied to find the optimal sequence for this type of problems. We now proceed to solve type 2 job sequencing problem, that is processing of n jobs through 3 machines. Suppose that n jobs are to be processed on 3 machines A, B and C in the order A, B, C. The list of jobs with their processing times on 3 machines A, B, C is given below. There is no direct method of sequencing n jobs on 3 machines A, B and C. So, we will convert the 3 machine problem to a 2 machine problem, and we can find an optimal solution of the problem if either or both of the following conditions hold. Condition 1, the minimum processing time on machine A is at least as great as the maximum processing time on machine B, that is minimum T1j is greater than equal to maximum T2j for j equal to 1 to up to n. Condition 2, the minimum processing time on machine C is at least as great as the maximum processing time on machine B, that is minimum T3j is greater than equal to maximum T2j for j equal to 1 to up to n. To find the solution of the problem, we follow some algorithm. Step 1, examine the processing times of the given jobs on all 3 machines, and if either one or both the following conditions hold, then go to step 2, otherwise the algorithm fails. Step 2, Introduce two fictitious machines, say G and H, with corresponding processing times given by Tgj equal to T1j plus T2j, j equal to 1 to up to n. That is, the processing time on machine G is the sum of the processing times on machine A and B. Tij is equal to T2j plus T3j, j equal to 1 to up to n. That is, the processing time on machine H is the sum of the processing times on machines B and C. Step 3. Determine the optimal sequence for n jobs and 2 machines equivalent sequencing problem with the prescribed ordering GH in the same way as discussed earlier. Now, let us take an example and see how this algorithm works. Find the sequence that minimizes the total time required in performing the following jobs on 3 machines in the order A, B, C. Processing times in hours are given in the following table. Since the condition minimum Taj is greater than or equal to maximum Tbj is satisfied for all j, the given problem can be converted into a problem of 5 jobs and 2 machines. And for this, we will introduce 2 dummy machines G and H, and the processing times on the dummy machines G and H can be obtained as Tgj equal to Taj plus Tbj and Thj equal to Tbj plus Tcj for j equal to 1 to up to 5. The following table shows the processing times on machine G and H. Now, since the problem is converted to 5 jobs and 2 machines, we can easily apply Johnson's algorithm to find the optimal sequence, and the optimal sequence is obtained as 3, 2, 5, 1 and 4. Now, for this optimal sequence, as before, we can find the minimum elapsed time as 51 hours and the idle time for machine A as 9 hours, idle time for machine B as 31 hours and idle time for machine C as 19 hours. In this module, we have discussed the basic terminologies and principal assumptions of job sequencing problems, and we have discussed 2 types of job sequencing problems. Type 1, that is processing of n jobs through 2 machines, and type 2, that is processing of n jobs through 3 machines. We have also taken some examples to show how Johnson's algorithm can be applied to find the optimal sequence in this type of job sequencing problems. With these comments, we end this module.